once again, we're going to change our focus to a different aspect of our physics. If we were to visit all of the various areas of physics in this course, we would have to hang out well into the months ahead. So we limit ourselves and we choose here at the end to investigate the phenomenon of light. The fancy term that I'll be using over and over again in this discussion for light is electromagnetic radiation. The first time that you really considered this in a scientific way might have been when you were taking a course in biology, presumably before taking a course in physics, when you were told that plants obtain their energy from sunlight. Plants have the chlorophyll and the many biological processes that go on in the leaves, the stems, and the roots of the plant, taking up the water, exchanging oxygen and carbon dioxide with the atmosphere. All of those biological processes begin with a simple statement by your biology teacher that plants get their energy from sunlight. Well, if you're a student of mine, I would hope that at a minimum, you know what I'm going to say. If you tell me that sunlight has energy, I'm going to say, what do you mean, energy? And of course, since we've been studying together, that has an answer. The answer to that question is, well, that somewhere there's a number that you can calculate that has the remarkable property that it remains the same, unchanged, or that it changes predictably no matter what occurs. That's how we define energy. And when we talked about energy in the past, I alluded to the energy associated with light. Well, in today's discussion, I hope to organize the ideas that we understand about electromagnetic radiation to the point that I can come to an equation, at least convince you that it's possible to calculate the number of joules associated with that. So I'd better make a start, and it begins with just a rational, logical discussion about the nature of light itself, and just a little bit of historical context, if you don't mind, because it's quite remarkable that Isaac Newton, while he was busy organizing the ideas of inertia, force, and action-reaction that are really the basis of all of our classical physics, that he was also busy investigating light. There's a famous portrait of Isaac Newton standing in the middle of a drawing room somewhere, and he has allowed a pinhole of light to come through a screen covering the window, and that white light impinges upon a prism and is separated into the many colors of the visible spectrum that you would probably at this moment refer to as the rainbow. Isaac Newton was interested in the nature and behavior of light. And he came to what at the time seemed like a very odd conclusion. Newton expressed that he felt that the behavior of light could be explained in the context of a stream of particles. Imagine I have a flashlight and I turn it on and I shine it at you. Newton's idea was that those particles would come flying at you and you would interact with those particles as they arrived. It was not a popular idea in Newton's time. Of course, he was extremely successful as a scientist, even in his own lifetime. But there were members of the scientific community at the time who thought that his idea that light came in small bundles, known as corpuscles, which is a word that is also used in biology for small droplets or cell-like structures, that a corpuscular theory of light did not make sense when there was a perfectly good explanation of light in the context of waves. But of course, I can see the effects of light when it interacts with matter, but the light itself I do not see. Even if you're out of doors on a day that has some clouds, some overcast, you say, look, there's a ray of light. The only reason why you see the ray of light shining through the clouds is that that light is interacting with water molecules suspended in the air. You can't see light unless it interacts with the rods and cones inside of your eyes, creating the sensation of vision. So it's very difficult to imagine the natural state of light. Newton imagined it was corpuscles. This next character here, James Maxwell, think around 1890, 1895. He did a remarkable thing. He took the phenomenon of electricity and magnetism and the equations associated with them, and he combined them together to a final set of equations that are so famous that they are referred to everywhere as Maxwell's equations. In fact, on any day in this room, if you felt yourself distracted you might have looked to the window and seen the 4 equations written there. They are Maxwell's equations. If you had considered getting a physics tattoo, that would be a tremendous one. Because those 4 equations formulated by Maxwell describe the entire behavior of electricity and magnetism. 4 equations only. And once you become accustomed to the mathematical notation in which they're expressed, they are very simple. Going one step forward, Maxwell took those 4 equations and smashed them together and created an equation that described electricity and magnetism as a wave. It's difficult for me to express to you how crushing a victory this was for Maxwell. And at the time, in our science, it was believed that he had answered the question of electricity and magnetism completely, that there was nothing else to learn, that it was over, that the theory had been put completely to bed. Electricity and magnetism, light, was a wave. Well, when you get to that sort of point where you imagine complete victory, when you imagine that it's all over, you know the very next thing that happens, another shoe drops. Sometime around 1905, Albert Einstein revealed to the world that it was not possible to explain every observed phenomenon in the context of light as an electromagnetic wave. That we would have to allow for the possibility that light had a kind of particle-wave duality. Particle-wave duality is really a pop culture term. You can find it all over the internet. Folks love it. But to me, and this is, you can tell, I think, by the way that I'm presenting it, it's a little bit of a pet peeve of mine, that I think it's misrepresented. Particle-wave duality, the implication is this: sometimes light behaves as a wave, and some other times it behaves as a particle. I believe that that is completely incorrect. And what I would like to just subtly place in your mind, that is in fact what's going on, is that sometimes when we observe the behavior of light, it has behavior that reminds us of what we understand about waves, like waves on a rope, or waves on water, or the waves that are the sound of my voice. And there are other instances where the behavior of light reminds us of particles, of atoms, of marbles, of planets and comets. That it has both of these behaviors simultaneously, and I want to, as I say, subtly place in your mind the idea that there is a third way of being, invisible and intangible, that is the way of being of light. Now, the trick of that is you can't actually see the light, it's intangible. So in order to convince you of this, you need to see the experimental results, and it's easy, it turns out to be easy, to convince someone that you can't just think of light as a wave, and you can't just think of it as particles. But for the purpose of today's discussion, I'm going to do both. I'll first imagine light completely as a wave, exactly as Maxwell would do. And then at the end, I'll talk about why I must also imagine it as a particle. So to understand the wave nature of light, I have to have a bit of an idea about what it was that Maxwell was dealing with. Now I know, because we've already had discussions about it, that there exists in nature an electrical effect. And we've talked about it at length, where I said the electrical effect is described by the electrical force. I created a mechanism for that called the electric charge, and I said that the electric effect was so strong and the charges so numerous that it was most convenient to describe that in the context of an electric field. Here, I've written capital E, the electric field. Be careful, because I said right at the top that I was interested in the idea that sunlight has energy, and energy is also capital E. There's a big danger here of confusing the quantities. Here, I'm talking about the electric field, which is a vector. The harpoon alone helps me out there because energy is a scalar. The electric field in newtons per coulomb, very familiar. There is also a magnetic effect. Dig up rocks out of the ground, and they have strange effects on compass needles, and they have curious experimental behavior that leads us to a magnetic force. And while there is no magnetic particle, we imagine a magnetic field, B. What a strange thing that the magnetic field is called B. But as I say, the nature of our universe is many-faceted. And so there are many phenomena to describe, and there are only so many symbols to use. And so we're using B for magnetic field. And let's not worry too much about its units, but for the sake of completeness, the units of magnetic field is the Newton meter per Coulomb squared, commonly known as the Tesla of magnetic field. So there are these two aspects, and when Maxwell comes to the problem, it seems like electrical effects and magnetic effects are completely unrelated to each other. For most of history, the human race believed that electricity and magnetism were two separate effects, unrelated to each other. But then it became apparent through experimentation around Maxwell's time that the truth was that if there was a region in time and space where the electric effect was changing, that the changing electric effect would create a changing magnetic effect. That is, a changing electric field creates a changing magnetic field. Similarly, a changing magnetic field produces a changing electric field. And so I can imagine an electromagnetic wave. I am thrilled to show you this on using the modern technology of this digital slide presentation here. Back in the day, I had to draw this thing by hand in chalk, and you're finding it a struggle to draw this image. That looks pretty good. To draw this by hand is a bit tricky. Here's what I have. I see two axes are presented here, one labeled electric field, one labeled magnetic field. The arrows that point upward along the electric field axis are electric field. And so I see an electric field that is increasing and then decreasing and then reversing completely such that it points downward and increasing and decreasing and so on and so forth. When you look at that, if you see sines and cosines in it, if you see that math happening in it, excellent, because the mathematics of sines and cosines definitely plays a role here. But the tricky bit is that perpendicular to the electric field is the magnetic field, here drawn along a magnetic axis perpendicular to the electric field axis, but it's doing the same thing. Because in a sense, and I'm not wild about using this vague terminology, but in a sense the electric field is feeding off the magnetic field, and the magnetic field is feeding off the electric field, and a consequence of that is that electromagnetic waves are self-sustaining. They don't need any kind of medium. They pass through empty space, which is critically important to biology. Because if you'd like to make the claim that plants get their energy from the sunlight, you immediately appreciate that between the sun and the earth is a vast chasm of empty space. Rope waves do not travel from the sun to the earth because there is no rope between the sun and the earth. Sound waves do not because there is no air. Water waves do not because there is no water. In the case of rope waves, sound waves, water waves, there is a medium through which the waves travel. Electromagnetic waves, because of the relationship between the electric and magnetic field, do not require a medium to travel. They travel through the vacuum of space. For a long time, in our physics, that was a difficult idea to accept. As soon as Maxwell convinced us 100% that light was a wave, physicists immediately began imagining what the medium was. Waves on a rope, waves in the water, waves in the air. Electromagnetic waves, we supposed, would need a medium to travel through. The medium was discussed in the scientific community by everyone in the know. It would have to be incredibly intangible, non-reactive. It must be difficult to measure. It was called the ether, spelled strangely, A-E-T-H-E-R. Why isn't it on the slide? Because in that span of time when the ether was proposed, an experiment was devised to verify its existence. Look, we know the ether's there. We just need someone to create a clever experiment that proves it. And two cats named Michelson and Morley famously devised an incredibly precise experiment that was going to make them famous because it was going to verify the existence of the ether. And they got a completely negative result. Nothing. The expectation of ether, the medium through which light travels, failed utterly. It is probably the most spectacular and important null result in a scientific experiment in human history. Electromagnetic waves travel through space with no medium whatsoever. But where do the electromagnetic waves come from to start with? Like, how do you create one? Well, the answer turns out to be the same as all other waves. Sure, there's no medium, but if I want to create waves on a rope, I tie one end of the rope off and I grab hold of the other end and I vigorously shake it up and down. I did it as a demonstration previously, you might remember. And the frequency of the waves that I get was equal to the frequency of the wiggling of my hand creating the waves. If I want to create waves in the water, I'll simply get a body of water and poke my finger in the water, and that will create waves that travel across the surface. The frequency of those waves equal to the frequency of my poking at the water. If I want to create sound waves, which I need to do to communicate this physics to you today, I push air across my vocal cords that vibrate and push and pull on the air with the frequencies that are musically the dulcet tones of my lovely voice. In order to create electromagnetic waves, I can simply do this. Take a plastic wand, as I've demonstrated before, and rub it with fur. Then I claim that that plastic wand is negatively charged. If I hold it very still in the air, I know, by agreement and experimentation, that it creates an electric field. But if I hold the wand still, that electric field is not changing in time. So I have to accelerate it, quite literally. Take the wand and wiggle it. When I wiggle it, I create a changing electric field because it's the charges on the wand that create the electric field, and the charges are on the wand. If I accelerate the wand, then the charges accelerate. That's a change in the electric field in the vicinity of the wand, which creates a changing magnetic field. And the change of that magnetic field creates a changing electric field, and so on. And the wiggling of the wand creates electromagnetic waves with a frequency equal to the frequency of the wiggling of the wand. Even though there's no medium, the creation of electromagnetic waves works the same. So to create a radio antenna, I have a tall, essentially a rod of metal that is full of electrons, and I push and pull on those electrons with some clever electrical circuitry that I've connected to the system. And those electrons go up and down, and the wiggling of the electrons creates radio waves that travel out over the land, delivering you your news, weather, music, and sports. The signal modulated in such a way to convey the radio signal in terms of the electromagnetic wave and the information associated with the broadcast. I think it's well understood that every object in the universe has a temperature, and I believe that we learn in our chemistry classes that temperature is the measure of the average internal kinetic energy of a substance. An object like yourself, or the table, or the earth, or indeed the sun, has a temperature because the atoms and molecules that make up material substances are vibrating. And because they're composed of charges, those charges are vibrating. And when the charges accelerate, they emit electromagnetic radiation. As it happens, you, right now, are shining light into the room. You have a temperature about 98.6 degrees, right, if you're healthy? I don't think that's really true anymore. They're changing the actual official human body temperature because I believe it's lowering. I think we're evolving to have a lower body temperature. But at any rate, you've got a temperature, and that temperature is due to the vibration of all of your molecules, and you are emitting light. In fact, about 100 watts of light, which is why when people sit near you, they feel warm. Your light is shining on them. I won't heat you up to the point that you glow, but I think you know that I could stick a piece of iron in a fire, and when I pull it out, it's hot. If I look at it with a special set of goggles on, infrared goggles, I can see that because it is hot, it is emitting electromagnetic radiation. If I stick it back in the fire and wait a while, if I pull it out, I can see that it actually glows. The frequency of the vibration becomes so high that it creates a light with a frequency that stimulates the rods and cones of the human eye, and I can see it in terms of visible light. Another thing that you learned in chemistry, apparently chemistry was worth something after all. A thing that you learn in chemistry is that matter is composed of atoms, and those atoms have protons, and in orbit of those protons are electrons. And the electrons in the atom organize themselves in states. And you were probably told that the electrons in those atoms can change state, either gaining energy and increasing their state, or losing energy and dropping their state. When electrons in atoms lose energy, they emit electromagnetic radiation. A good example of this is a neon sign. In the glass tubing of a neon sign, there is a noble gas trapped. Those are the gases down the right-hand side of the periodic table. And when the voltage is high enough, the gases in a neon sign glow with very pretty lights of specific colors because the frequency of the light is associated with the electronic transitions in atoms, which are very specific, producing all of these pretty colors. So these are basically all of the ways which electromagnetic radiation can be produced. I've left two off the slides. I'm now realizing I left off lasing that produces laser light. I've left off phosphorescence. I've left off bioluminescence. But those additional ways of producing light are ultimately, when you investigate them, based on these major three ways. It comes down to acceleration of charges creating electromagnetic radiation in the form of waves. So of course, it happens all the time, and I wonder if maybe, I would like it very much if you've gotten this impression in your head, is that what happens every time he talks about physics, he talks about the ideas, and at some point it turns into math, because we're going to have some equations that we can use to calculate. Yeah, sure, because there are rational, logical, mathematical relationships that create our physical laws. The things that we can measure organize themselves this way, and it always happens. Well, I can tell you I'm not looking forward to these new wave equations you're going to create for electromagnetic waves. Well, good news, because I'm not going to do that. Electromagnetic waves follow very much the same mathematical rules as waves on a rope, waves on the ocean, waves of sound. It's all waves, waves, waves. And so an equation that you are already familiar with, because we've talked about sound waves, is that the speed of a wave is equal to its frequency times its wavelength. Now, you may have heard that in the case of light, there is a particular speed of interest. The speed of light is commonly given the symbol c and is 3 times 10 to the 8th meters per second. Take a moment to appreciate, if you have not yet, that is spectacularly fast. Spectacularly fast speed. In fact, you may even heard rumors to the effect that that is the ultimate speed in the universe and nothing goes faster than that. I want to really quickly let you know that because we're specifically investigating light, there's a caveat on this. It gets an asterisk. 3 times 10 to the 8th meters per second, c, is the speed of light in the vacuum of space where there is effectively no matter. No atoms, no charged particles in that region of space. It's the speed that electromagnetic waves have when they are traveling through nothing at all. And I have to point that out particularly because we are going to take an interest in light that travels through the air. The atmosphere of the Earth, for example, will be interested in light traveling through water, through glass, and even through diamond. When light interacts with matter, the interaction between light and matter takes time. And that time slows the light down. So I'll just take a moment to appreciate that when I say that the speed of light is 3 times 10 to the 8th meters per second, I'm referring specifically to the speed of light in vacuum. Now, a bit of a payoff, because I said that plants receive their energy from the sunlight because the sunlight contains energy. What do you mean, energy? I mean, there's a number that you can calculate that has this remarkable property. And so this slide really exists for the sole purpose of fulfilling that promise. I'm not particularly interested, for the moment at least, in calculating how much energy there is in sunlight. All I want to do is suggest to you that you weren't being lied to. There is an equation for it. If I'm interested in energy associated with the current that flows through a resistor. A bit of a problem that I have is that the current is flowing through the resistor continuously. So I can't talk about a particular number of joules. Instead, I talk about the power, the rate at which the joules go through the thing. I'll do the same thing here. It's true that if I take my pointer here and I produce a brief flash of laser light, pew, and it appears for an instant and disappears, there is a way that I could calculate how many joules of energy are in that little flash of laser light. By the way, where did the energy come from? My pointer has a battery in it. There's a chemical reaction that takes place to separate charge, turning chemical potential in the battery into potential difference in the circuit, which then goes through the light emitting device in the thing and produces the laser light. Energy, 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 one to the other. Well, while I could do that for a burst of light, sunlight is rather continuous. If you go outside to get a tan, the amount of energy you receive from the sun depends certainly on how much time you spend outside and what your cross-sectional area is. So for my purpose, I'll say, or I'll describe it as an energy per volume on average, which is why here on the left-hand side of this new fancy equation I have, I've written lowercase u. Uppercase u is potential energy, we used previously in our notation. Lowercase specifically means per volume. It's what we call a specific quantity. We use a lowercase. And I put a bar on top of it. That's not the first time I've done that. When I described the average velocity, I put a bar on to say average. So this means the average energy per unit volume of sunlight is equal to 1/2, that's fine, a new constant of the universe. Charlie, please, no more constants. Oh, okay, hang on. It's called the permittivity of free space. Epsilon, another Greek letter, I know it's like we're collecting them. Epsilon naught, as it turns out here, 8.85 times 10 to the minus 12th, which means nothing to you. It's not a new constant. Remember back to when we described the electric force and the electric field, there was a constant in front called Coulomb's constant, K, associated with that. Epsilon naught is simply related to K. Epsilon naught is 1/4 pi times the Coulomb constant, which we're already familiar with. That's that 9 times 10 to the 9th, used to calculate the force and the field. So here I have this equation, and I'm not particularly interested in calculating it necessarily. We might do it as an exercise, but here it is, 1/2 that constant times E naught. That capital E there is not energy, it's electric field. Remember that electromagnetic waves are waves of electric and magnetic fields. And so the E that appears here, and in particular E naught, is the maximum value of the electric field. In my E and M wave, the electric field increases and decreases, becomes negative, increases to a maximum negative value, and then this, that, and the other, all back and forth. E naught is the maximum value that obtains. And so my energy is 1/2 epsilon naught E naught squared. I wonder, and I guess I have these little secret hopes, that you look at that and go, it reminds me of 1/2 mv squared, the kinetic energy. Or maybe you say to yourself, well, it reminds me of 1/2 kx squared, the spring potential energy. Well, that's not a bit of silliness on your part. It's true. It reminds me of that as well. It turns out there are so many linear relationships in our universe, and when we integrate those linear relationships, you get a little 1/2 kx squared action happening on average. The patterns of the universe repeat themselves, and that's an encouraging thought, because the universe is a complicated place, and so it's nice that the patterns repeat themselves. It makes me feel like we have a chance of having an ultimate description sometime far off in the history of mankind. Waxing too poetic now, I want to change from describing light as an electromagnetic wave to describing it as a particle. It's a very different picture, because instead of being everywhere in space all the time, the wave is now localized as a little particle of light. So the stream of light that comes in through the window or is emitted by the lights in the room or coming off of your computer screen is a stream of submicroscopic particles, still electromagnetic in nature and fundamentally interacting with matter in interesting ways. But in 1905, Albert Einstein was aware of some experiments that caused trouble for electromagnetic waves. In particular, it's called the photoelectric effect. It happens with various metals and various wavelengths of light. For example, if I take a piece of zinc metal, and I shine ultraviolet light on the metal, electrons are ejected from the metal. It's an experimental observation. It's easy to do. It's a fact. When you try to explain that experiment as waves of light hitting the metal, it becomes impossible to explain why electrons would be ejected. It does not work. The ideas aren't compatible. Albert Einstein realized that if you instead imagine light as a particle, the idea that a particle of light goes into the zinc and like a billiard ball boosts an electron out of the metal not only makes sense, it completely describes the physical phenomenon. So in 1905, Einstein proposed that there were certain critical experiments that could only be described in the context of particles of light that we call photons. And he gave us the equation for the energy of a photon. How incredibly simple this equation. The energy of a photon. I'm not wild about the fact that I've written subscript photon under here, but I felt that it was necessary because I'm not talking about electric field here. This is not the electric field of a photon. It's the energy possessed by a single photon of light is proportional to the frequency of the photon. As a student of physics, it'll be a valuable thing for you going forward to appreciate that the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. It's not a hard concept to remember because I think that most of you witnessed me here up in the front with a piece of rope in my hand trying to vibrate it at high frequency. It's very difficult for me to make the rope wiggle at high frequency because to do so takes a lot of energy and perhaps I'm too lazy for that endeavor. In order to make it go at low frequency requires very little energy. And Einstein's equation for photon energy sort of bears that out. The energy of a single photon is an experimental constant of proportionality times the frequency. So if the frequency increases, the energy increases. If the frequency decreases, the energy decreases, and then there's this constant. I would hope that you had heard of this constant before. It is very, very, very famous in our science. It's called Planck's constant. Planck, Max Planck, was a contemporary of Albert Einstein and a big supporter of Albert Einstein. Albert Einstein's ideas were very out of the box and not always palatable to the mainstream physics at the time. Max Planck was a very well-established physicist, particularly in Germany, and he wrote many letters around the physics community saying, we should be listening to this Albert Einstein guy. He knows what he's talking about. So the experimental constant that makes it all work out is called Planck's constant. It's given the symbol H. Why not P for Planck? Because P is momentum. You see the same problem all over the place. H is Planck's constant. And here, I've written it in a curious way. 4.14 times 10 to the minus 15th, okay, whatever you say, that's a number that came from an experiment. EV seconds are the units that I put on here. EV second. At first blush, a physicist might look at my slide and say, you probably should have put 6.62 times 10 to the minus 34th joule seconds, because your students will be expecting the energy to be measured in joules. Well, you see, the thing is that the energy of a photon is an incredibly small amount of energy. The energy of transition inside of an atom is an incredibly small amount of energy. And a joule, in comparison, is a stupid large quantity of energy. Because joules were the unit of energy applied to our physics when our physics had not become microscopic. When I want to describe microscopic behavior, photons and atoms, I'd like to use a smaller unit of energy. The EV represents the electron volt. It's quite simple. 1 electron volt is the amount of energy required to move an electron through a potential difference of 1 volt. Earlier in our course, we discussed how electrical energy was Q times V. Well, if the charge is 1 electron and the voltage is 1 volt, that's an electron volt. 1 electron volt is 1.6 times 10 to the minus 19th joules. An electron volt is a tiny, 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 like infinitesimally small compared to the size of a joule. But electron volts are super when you're doing calculations of photons and their interactions with atoms. And so I choose, instead of using joule seconds here, to use electron volt seconds because I'm probably going to work out some examples, and those examples are going to be really, really tiny. This Planck's constant, and indeed Einstein's relationship for the energy of photons, is very near and dear to my heart because it intersects with a branch of physics that is really my area, which is known as quantum mechanics. We won't study quantum mechanics in our course. There's a separate course, in fact, 3 separate courses for that. But the idea here is that light comes in little parcels. Those little parcels are sometimes referred to as quanta, which is where the discipline of quantum mechanics gets its name. Oh shit, bro, that was 40 minutes.
Mm-hmm.